Hi, welcome. In a series of videos, I will be covering shortcuts and tricks for evaluating series in summation or sigma notation. For the content of the series, we are going to be looking at introduction to the sigma notation, what it is, the various parts of the symbol and what they stand for. We would also look at the properties of sigma notation and their applications. Then we'll look at standard formulae and how they are applied in solving questions. We would also be interested in the arithmetic, geometric, and alternating finite series. Then we would also look at the use of the Morse theorem in evaluating some series, especially those that involve trigonometric functions. And at the end, we'll look at partial sums of telescoping infinite series and the method of difference for evaluating those that converge. So for the first part, we'll look at the introduction, properties of sigma notation and their applications, and then standard formulae and their use. Then in the second part, we'll look at arithmetic, geometric, and alternating series. And then in the last part, we'll look at the use of the Morse theorem and then partial sums of telescoping infinite series and the method of difference. So the series would contain 3 parts as I've already partitioned. So to begin, we have to note that the sigma notation is a compact or condensed way of writing down a long sum of terms of a sequence, usually called a series, using this symbol, which is actually a Greek capital letter called sigma. Now consider the series 2 plus 4 plus 6 plus 8 plus 10, and the series can actually be written following a certain pattern. You can see that the numbers have a characteristic in that they are all multiples of 2, so that 2 can be written as 2 into 1, 4 as 2 into 2, 6 as 2 into 3, 8 as 2 into 4, and then 10 as 2 into 5. You can observe that the numbers have a pattern. They are multiples of 2 or even numbers. In fact, they are of the form 2r, where r equals 1, 2, 3, 4, or 5. Now this series is easy to handle because it's a short one. There are cases where the series will be a very long one, so this series of even numbers could extend to up to 10,000 or even more, and so we would be having the problem of time and space to handle it. So in order to save time and space, the sum of the terms above can be written as summation from r equals 1 to 5 of 2r. And actually this is the sigma notation of the series that we are just from seeing above. Now before we proceed, we need to look at the different parts of that symbol and what they stand for and the role they play in evaluating the series in general. So the sum tells us to add terms of the form 2r from r equals 1 to r equals 5. So you have this part here. You have to sum the terms from when r is 1 to when r is 5, and you get the terms by substituting them in this function that appears after the sigma notation. So when I substitute r equals 1, I will get the first term, which is 2. When I substitute r equals 2, I will get the second term, which is 4. When I substitute r equals 3, I will get the third term, which is 6. When I substitute r equals 4, I will get the fourth term, which is 8. When I substitute r equals 5, I will get the last term, which is 10. Now r is the index variable and it's usually an integer. It is actually a dummy variable because I can replace that r by I or k or j or n or any other variable of my choice. So for instance, I could now instead have summation from I equals 1 to 5 of 2i, and that wouldn't change the fact that I will still generate the series 2 plus 4 plus 6 plus 8 plus 10. If I change it to W, for instance, summation from W equals 1 to 5 of 2W, it will still generate the same series without any difference in the number of terms that have appeared there. Any variable that behaves in this way is called a dummy variable. Now, the function 2r is called the argument or the summand of the summation, and is usually a general or explicit formula for generating the terms in that series. We note that this first value of r, 1, is the lower limit, while the last value of r, 5, is called the upper limit. Now, there are situations where this series would have continued up to a certain last value, and so we would have summation from r equals 1 to n of 2r equals 2 plus 4 plus 6 plus the other terms and then plus 2n. And in this case, we are actually dealing with the nth partial sum, because this series could continue indefinitely. There are also situations where the series would be in such a way that we have summation from r equals 1 to infinity of 2r. In that case, we don't have any last term, and that simply means the series continues up to infinity. We'll be talking of the infinite sum, or the sum to infinity, and it will have a finite value if at all it converges. In the next part, we'll be looking at a finite series, and a finite series is actually the sum of a sequence that has a countable number of terms. Consider the series summation from r equals 1 to n of f of r, which implies that we should have the terms f of 1. When you substitute the lower limit, you get the first term. When you substitute the next consecutive integer, 2, you would get the next term, and when you substitute the next consecutive integer, 3, you will get the third term, and so on, until when you substitute the upper limit, which should give the last term as f of n. When you sum all these terms, you will get the nth partial sum, which is called Sn. An example, summation from r equals 1 to 5 of 2r plus 1 would actually be 3 plus 5 plus 7 plus 9 plus 11, which gives 35, and is called the sum of the first 5 terms. Note that the terms are generated by substituting consecutively the integers from r equals 1 to 5 in the summand or the argument of the summation. So when r equals 1, you get 2 into 1 plus 1, which gives 3. When r equals 2, you get 2 into 2 plus 1, which gives 5, and so on up to when r equals 5, where you have the last term. You substitute 5 in the summand, you get 2 into 5 plus 1, which gives 11. Now, we could have a situation where the series does not begin from r equals 1. This time the series begins from r equals 0 up to n. So in this case, the first term would be f of 0. When r equals 0, you would get the first term. When r equals 1, the next integer, you will get the second term, and so on up to when r equals n, where you will now get the last term. We have to note here that in the series up, we had the sum from when r equals 1 to n, and it gave us n terms. So we're looking for the sum of the first n terms. In this one, there is an additional term. So when the series begins with r equals 0, there will be an additional term. So in this case, we are not dealing with the nth partial sum, but the n plus 1th partial sum. So when the series begins with r equals 0, you would be having n plus 1 terms instead of n terms. Take note, because sometimes to evaluate such a sum, students have difficulties dealing with the number of terms. When the lower limit is 0, the number of terms is no longer n, but n plus 1. An example, summation from r equals 0 to 5, the same series that we had up, so that we can compare and see what is happening. When r equals 0, you get the first term. 2 into 0 plus 1 would give 1. Then when r equals 1 up to 5, we get the series that we generated up here. And so overall we have 1 plus 3 plus 5 plus 7 plus 9 plus 11. As you can see, 1, 2, 3, 4, 5 and 6 terms. That sum gives 36, and it is the sum of the first 6 terms as opposed to the sum of the first 5 terms when r was beginning with 1. We have to note that generally the series summation from r equals 1 to n of f of r has n terms. So when the lower limit is 1, the upper limit would give you the number of terms, and when the lower limit is 0, you have to add 1 to the upper limit to get the number of terms. The number of terms for the finite series summation from r equals a to b of f of r is actually b minus a plus 1, where b is greater than or equal to a. So we note that generally for a series that is written in sigma notation, the upper limit is always equal to or greater than the lower limit. Already at this point, you can have a multiple choice question asking you the number of terms in a series that is written in sigma notation. So we have this question: the number of terms in the series summation from r equals 7 to 150 of r into r plus 1 is a 150, b 143, c 144, d 7. You can see that to write out this series term by term would be so difficult because there are many terms that are involved. So we now use the formula which says is the upper limit minus the lower limit then plus 1. So 150 minus 7 would give 143. Then when you add 1, you have 144. So the correct key should be C. Now we'll be looking at the properties of the sigma notation, and we'll start by looking at the examples and then making general conclusions. Consider the series summation from r equals 1 to 5 of 3. You can notice that it is the summation of a constant. So we are summing 3 from a count of 1 to a count of 5. So we expect to have 3 plus 3 plus 3 plus 3 plus 3. So we have summed up 3 5 times. So the result is simply 5 into 3, which gives 15. So generally we can say that summation from r equals 1 to n of k would be k plus k plus k plus k plus k. Actually we are summing up k n times, and so the result is simply n times k, just like we had the case of summing 3 5 times and the result reduced to multiplying 5 by 3. So this is a general formula for summing up a constant k from a count of 1 to a count of n. An example: summation from r equals 6 to 20 of 10. Actually, to evaluate this, we go back to the general formula. Summation from r equals 1 to n of k is simply the number of terms, the number of times k has been summed, times k. So when you have this case where r is not beginning at 1, you simply find the number of terms and then multiply by the constant. So here we are summing 10 from a count of 6 to a count of 20. So actually the number of times that we are supposed to sum that 10 would be 20 minus 6 plus 1. The value of that sum then would be 10 into the number of terms. We get the number of terms by the upper limit minus the lower limit plus 1. So 20 minus 6 plus 1 would give 15. So the sum would be 10 into 15, which gives 120. Further, consider this other case: summation from r equals 1 to 5 of 4r. If we generate the terms, we get 4 into 1 plus 4 into 2 plus 4 into 3 plus 4 into 4 plus 4 into 5. summing the products of 4 and the consecutive integers from 1 to 5. We can notice that all the terms have a common factor of 4. We can factorize 4 to have 4 into 1 plus 2 plus 3 plus 4 plus 5. And this can then be written as 4 into the summation from r equals 1 to 5 of r. We can then generalize that when you have summation from r equals 1 to n of a certain constant times the summand, it is the same as the constant times the summation from r equals 1 to n of the summand. Now consider this other example, summation from r equals 1 to 3 of r plus r squared. So the summand is the sum of two terms. We'll then generate the terms by substituting 1. We get 1 plus 1 squared. Substituting 2, we have 2 plus 2 squared. Substituting 3, we have 3 plus 3 squared. We can actually group these terms into those that are not squared and those that are squared. So we would have in the first term 1 plus 2 plus 3, and in the second term 1 squared plus 2 squared plus 3 squared. And we can notice that the first term is the summation from r equals 1 to 3 of r, while the second term is the summation from r equals 1 to 3 of r squared. So a general formula can then be written as summation from r equals 1 to n of f of r plus or minus g of r being equal to summation from r equals 1 to n of f of r plus or minus summation from r equals 1 to n of g of r. Actually, this property is simply telling us that the summation sign is distributive over addition and subtraction. So if you have, for instance, a polynomial function which has many terms, you simply distribute the sigma notation to each of the terms before evaluating. Now we proceed to standard formulae. We have the formula for the sum of the first n natural numbers, which is summation from r equals 1 to n of r equals n into n plus 1 all over 2. The function f of r is generating the terms, while the function g of n is generating the sums of terms. So when r equals 1, I get the first term, and when n equals 1, I get the sum of the first terms. So if you put r equals 1, you will get 1 as the first term, and when you put n equals 1, you get 1 into 1 plus 1 over 2, which gives 1 times 2, 2 over 2, and it gives 1. And that is true because the sum of the first term is simply the first term. Now if you substitute r equals 2, you get the second term. Then when you add the first term, which was 1, to the second term, which is 2, you get 3. So the sum of the first two terms is 3. Actually, you can get that sum of the first two terms by directly substituting 2 in the formula on the right, which is supposed to be generating the sum of the first n terms. And so when n equals 2, you get 2 into 2 plus 1 over 2, and you would have 6 over 2, which gives 3, the same sum we had by generating the terms and adding them individually. We also have the formula for the sum of the squares of the first n natural numbers, which is given as summation from r equals 1 to n of r squared equals n into n plus 1 into 2n plus 1 all over 6. And again, it operates in the same way as I've explained for this one. R squared generates the terms in that series, while n into n plus 1 into 2n plus 1 all over 6 generates the sums of the first n terms of that series. Then the last formula we are supposed to look at is the sum of the cubes of the first n natural numbers, which is given as summation from r equals 1 to n of r cubed equals n squared into n plus 1 all squared all over 4. And one thing we have to note is that in all the three formulae, the lower limit is 1. So you have to be very careful then when evaluating series in which the summand is r r squared or r cubed, or a polynomial that involves terms having r squared and r cubed, in that if the lower limit is not 1, you would have to use the following tricks. The first one is that summation from r equals 0 to n of f of r can be broken down into f of 0 plus summation from r equals 1 to n of f of r. So when the lower limit is 0, you first write out the term in which r equals 0 and then plus summation from r equals 1 to n of f of r. From there now you can apply the appropriate formula to evaluate this other sum before adding f of 0 to the result. So that is how you will be treating this case. There can be also a case where you neither have 0 nor 1, for instance the lower limit being 10. So in a situation where you are summing from r equals k, a bigger number, to n of f of r, you actually first take summation from r equals 1 to n of f of r. So you take summation from r equals 1 to the upper limit of f of r, then minus summation from r equals 1 to the next lower integer of the lower limit k, which should be k minus 1. And from there you can now apply the formula in the various parts without difficulty. So we have to note that the above formulae are useful in evaluating series when the argument of the summation is a polynomial. We take example, evaluate summation from r equals 1 to 10 of 2r minus 3 all squared. You can see that the summand is a polynomial. So we actually have to start by squaring 2r minus 3, and we will then have 4r squared minus 12r plus 9. One of the properties we saw is that the sigma notation is distributive over addition and subtraction. And so we'll distribute the sigma notation to each of these terms so that we get summation from r equals 1 to 10 of 4r squared minus summation from r equals 1 to 10 of 12r plus summation from r equals 1 to 10 of 9. And again, one of the properties say if there is a constant term multiplying the summand, you can factor it out of the sigma notation. So in the next step we have 4 summation from r equals 1 to 10 of r squared minus 12 summation from r equals 1 to 10 of r plus summation from r equals 1 to 10 of 9. From here now we'll bring in the formula for summation from r equals 1 to n of r squared, which says n into n plus 1 into 2n plus 1 all over 6, n being 10. We then have this term summation from r equals 1 to 10 of r squared to be 4 times 10 into 10 plus 1 into 2 times 10 plus 1 all over 6, and then minus 12 summation from r equals 1 to 10 of r, and the formula for summation from r equals 1 to n of r is supposed to be n into n plus 1 all over 2. So n being 10, then that term should be negative 12 into 10 into 10 plus 1 over 2 plus the last sigma notation, which is summation from r equals 1 to 10 of 9. So the summation of 9 from a count of 1 to a count of 10, we are supposed to sum 9 10 times because there are 10 terms there, and so it would just be 10 times 9. We will then have that sum to be equal to 4 into 10 into 11 into 21 over 6 minus 12 into 10 into 11 over 2 plus 10 into 9, which gives 1540 minus 660 plus 90, giving a sum of 970. We take another example. Evaluate summation from r equals 101 to 200 of r. This is a GCE question. We note that the lower limit is not 1. So we are summing from r equals 101 to 200. Then in order to use the standard formula, we have to make sure that the lower limit begins with 1. So we now do a manipulation where we start by finding the sum from r equals 1 to the upper limit, which is 200 of that summand r, minus the summation from r equals 1 to 100, because we're interested in the sum from when r equals 101. So we have summed up from 1 to 200, then we have to subtract the undesired sum that we have included, which is the summation from r equals 1 to the next lower integer of 101, which is 100. So then apply the formula directly to have summation from r equals 1 to 200 of r, and the formula says n into n plus 1 all over 2, n being 200. We then get 200 into 200 plus 1 all over 2, minus summation from r equals 1 to 100 of r, where n now is 100, so that we get 100 into 100 plus 1 all over 2. And when we evaluate the two terms, we get 20,100 minus 5,050, which gives 15,050 as the sum. There is actually an alternative method for evaluating that series. We note that it is an arithmetic progression, because when you start summing from 101, you are simply summing integers consecutively from 101 to 200. That is an arithmetic progression, because consecutive integers always form an arithmetic progression with a common difference of 1. So here we are summing from r equals 101 of the function r. So that is why the first term would be 101 and the last term would be when r is 200, which gives 200, and then we have 100 terms. Very important. The number of terms will be very important in getting the sum of that arithmetic progression. Again, you get the number of terms by taking the upper limit minus the lower limit, then plus 1. So 200 minus 101 gives 99. When you add 1, you have 100 terms in that series. You can then use the formula for the sum of the first n terms of an AP, which is given as the number of terms over 2 into the first term plus the last term. So the sum of these 100 terms we are seeking to find would be 100 over 2 into the first term, which is 101, plus the last term, which is 200. This gives 50 into 301, which gives again 15,050. The result we had above using the standard formula. We take another example. Find summation from r equals 1 to n of r into 3r plus 1, simplifying your answer as much as possible. This is also a GCE problem. We note here that the question is asking us to find the nth partial sum of that series. And again, when you observe the summand, you discover that it is a polynomial, and so we'll be relying again on standard formula for finding that nth partial sum. Summation from r equals 1 to n of r into 3r plus 1 will be summation from r equals 1 to n of 3r squared plus r when you expand the r into the bracket. We then distribute the summation sign to have 3 summation from r equals 1 to n of r squared plus summation from r equals 1 to n of r. And we can then proceed to bring in the standard formula to have 3 times n into n plus 1 into 2n plus 1 all over 6, the formula for summation from r equals 1 to n of r squared, plus the formula for summation from r equals 1 to n of r, which is n into n plus 1 all over 2. So in the next step, when you cancel 3, you'll get n into n plus 1 into 2n plus 1 over 2 plus n into n plus 1 over 2. And proceeding, we can see that n into n plus 1 over 2 is common. Overall, when you divide each term by the common factor n into n plus 1 over 2, you will get 2n plus 1, which now gives 2n plus 2. and we can see that 2 is common in this last factor, which we can factorize, and we'll cancel with the 2 at the denominator, so that we get n into n plus 1 all squared as the nth partial sum of that series. So we can conclude that summation from r equals 1 to n of r into 3r plus 1 equals n into n plus 1 all squared. And we can actually verify that this is true. For instance, when r equals 1, we substitute 1 in the summand, we get 1 into 3 into 1 plus 1. There will be 1 into 3 plus 1, which gives 1 times 4, which is 4. And when you substitute 1 to get the sum of the first term, you get 1 into 1 plus 1 squared. 1 plus 1 squared is 2 squared, which is 4, and 4 times 1 is 4. So the sum of the first term is equal to the first term. If you verify the sum of the first two terms, the first term is 4. When you want the second term, you substitute the next integer, which is 2. 2 into 3 times 2 plus 1. 3 times 2 plus 1 will be 7. So 2 times 7 will give 14. So the second term is 14, and the first term we had was 4. So the sum of the first two terms would be 4 plus 14, which gives 18. And we can get that sum directly by substituting n equals 2 on the right hand side to have 2 into 2 plus 1 squared. 2 plus 1 gives 3, and 3 squared is 9. Then 9 times 2 would give 18. The same value we had when we had the terms individually and summed them up. So you can actually prove that this is true for all natural numbers n using mathematical induction. Another GCE question: find summation from r equals n plus 1 to 2n of r, simplifying your answer as much as possible. Again, we have to note that the lower limit is not 1, and so to apply the standard formula, we have to manipulate by having summation from r equals 1 to 2n of r minus summation from r equals 1 to n. That means the next lower integer of n plus 1, which is obtained simply by subtracting 1 from n plus 1. So when you subtract 1 from n plus 1, you get n. And we can now apply the formula so that we have summation from r equals 1 to 2n being 2n into 2n plus 1 all over 2. Since the upper limit is now 2n and not n, we have to replace n in the formula by 2n. That is why we have 2n into 2n plus 1 over 2 minus summation from r equals 1 to n of r, which the formula gives directly as n into n plus 1 all over 2. We can now proceed to factorize. N over 2 is common. You have n over 2, n over 2. So it's common. N over 2 factorize. You divide every term by that common factor. When you divide this term by n over 2, you get 2 into 2n plus 1, which gives 4n plus 2. And when you divide this other term by n over 2, you get negative of n plus 1, which gives negative n minus 1. When you simplify further, you get 2n minus n, which gives 3n, and then 2 minus 1 gives 1. So finally, we get summation from r equals n plus 1 to 2n of r as n over 2 into 3n plus 1. Now, we can also use summation of an arithmetic series to obtain that result. The first term should be when r equals n plus 1, and it will simply give n plus 1 as the first term, while the last term will be when r equals 2n, which simply gives 2n as the last term. Then the number of terms would be n, because 2n minus n plus 1 and then plus 1 would simply give n. We can then use the formula for the first n terms of an arithmetic series, which says Sn equals n over 2 into the first term plus the last term. The number of terms n over 2 into the first term n plus 1 plus the last term 2n, and we have again 3n plus 1, so that we get again n over 2 into 3n plus 1, the same result that we had using the standard formula.